Hello and welcome to the next lecture. So in this lecture we are going to discuss about the time response of a second order control system. Okay, so what is second order control system? The second order control system is one where the highest power of as in denominator is 2. Okay, so this for transfer this function is simply called as the second order control system. Okay, and the general expression of the for the transfer function of the second order control system, the block diagram is shown over here. You can see that and in the transfer function of this should become equals to what? Cs is the output upon the input. Okay, rs, this will become equals to omega n square upon s square plus 2 zeta omega n square plus, sorry, it's 2 zeta omega n, sorry, this is not square, this is s, plus omega n square. All right, the parameters zeta and omega n are what? So here zeta is simply called as a damping ratio. Zeta is called damping ratio. Okay, and what is omega n? Omega n is simply natural frequency of oscillation. Natural frequency of oscillation. Okay, so this is simply the second order transfer function. Okay, so what we are going to see, in this we have to see the time response of the second order system. So how we are going to find out the time response of the second order system? We can find it out by applying the unit step input, the unit ramp input, your impulse input. So first of all we are going to take and the only condition which we will see over here should be the time response of a second order control system subjected to a unit step input function. Okay, so we are going to discuss about this, that is the time response of a second order control system subjected to unit step input function. What is unit step input function? We have already discussed it earlier in the last lectures. Okay, so just take the output of the system. Output for second order system is given as output of system, which is second order system, is simply Cs is equals to Rs into omega n square upon s square plus 2 zeta omega n s plus omega n square. Okay, so here what we are going to take, here we are just going to take the input is a unit step function as the input, is a unit step function. So what is unit step function? Rt is equals to 1, and we all know that Laplace transform of Rt, if you are going to take Laplace transform of this, it will become Rs is equals to 1 upon s. So we are just going to put the value of Rs in this equation. All right, so just substituting this in the above equation, we will get the output Cs should be equals to 1 upon s into omega n square upon s square plus 2 zeta omega ns plus omega n square. Okay, so just breaking the above equation and just taking the partial fraction of this. So for this we need to do a bit of breaking, and we will get it like 1 upon s minus s plus 2 zeta omega n divided by s plus zeta omega n whole square, okay, plus omega n square 1 minus zeta square. All right, taking omega d as omega d, we are just going to take as omega n into under root of 1 minus zeta square. All right, so what should be the output? CS will become 1 upon s minus s plus 2 zeta omega n divided by s plus zeta omega n का whole square plus omega d square. All right, so we can rewrite the above equation. We can rewrite this above equation as CS. This will be equals to 1 upon s minus s plus zeta omega n divided by s plus zeta omega n whole square plus omega d square minus zeta omega n upon omega d into omega d upon again same terminology, s plus zeta omega n square. Sorry, this is square plus omega d square. All right, we are just going to take the inverse Laplace transform on both the side. So taking inverse Laplace transform, if you are going to take inverse Laplace transform of this, just write down like this. I am just adding in the above equation only Laplace inverse of this and Laplace inverse of this whole equation. Okay, this whole equation. All right, what we will get if we are going to take the Laplace inverse of CS? This will become CT Laplace inverse of 1 upon s 1 minus Laplace inverse of this equation s plus zeta omega n upon this. This will give us e to the power minus zeta omega n t, okay, into cos omega d into t, okay, minus zeta omega n upon omega d. This terminology comes over here, and Laplace inverse of this terminology will be e to the power minus zeta omega n t into sine omega d t. Okay, we will get this as the output. So since omega d is equals to what? We have taken it already as omega n under root of 1 minus zeta square. Okay, we are just going to write this, put this value in the above equation. In this equation, if we are going to put this value, and after doing some simplification, we will get 1 minus e to the power minus zeta omega n t divided by under root of 1 minus zeta square in bracket under root of 1 minus zeta square cos omega dt plus zeta sine omega dt. Okay, so this is what we are getting. So we are just going to put sine phi is equals to under root of 1 minus zeta square. Therefore cos phi will become zeta. Okay, then ct will become what? This above equation will become ct will become 1 minus e to the power minus zeta omega n t upon under root of 1 minus zeta square. Okay, in bracket sine phi cos omega dt plus cos phi sine omega dt. Okay, so ct will become what? Ct is equals to 1 minus e to the power minus zeta omega n t upon under root of 1 minus zeta square sine omega dt plus phi. Okay, so this is the output. So we know that since omega d is what? Omega n 1 minus zeta square. So phi will become phi from here will become phi should be equals to tan inverse of, we have the value of sine phi and the cos phi, so simply phi should be equals to tan inverse of 1 minus zeta square upon zeta under root of zeta square upon zeta. All right, so we can rewrite this equation as below. Ct will be equals to 1 minus e to the power minus zeta omega n t upon under root of 1 minus zeta square sine omega n under root of 1 minus zeta square t, okay, plus tan inverse of under root 1 minus zeta square upon zeta. This is what the value of Ct. So this is a simply mathematical elaboration. You can very easily solve it mathematically and you will get the output as this one. Okay, so this is what Ct we are getting. So as in the first order control system, we have write the error. Error is what? Et. Error is given by, in the last lecture we have discussed, so error is given by Et, and Et is what? Simply your RT minus Ct. So RT we have taken as a unit step response, so the value of the RT is simply 1. RT is equals to 1. So just put the value of RT is equals to 1 and you have the value of Ct in the above expression. So we will get Et as, after solving we will get Et as e to the power minus zeta. As you can see that in this expression when we do 1 minus this, so 1 and 1 should get going to be cancelled out, and the remaining expression I am writing over here minus zeta omega n t, okay, divided by 1 minus zeta square over here into sine omega n under root of 1 minus zeta square t, okay, plus tan inverse of 1 minus zeta square upon zeta. This expression we are getting as the error. Okay, so what is the steady state error? Steady state error is simply this, that when we are going to put the limit t tends to infinity. All right, so steady state error can be written as steady state error, which is what? ESS, which will be equals to limit t tends to infinity. Okay, and the value of Et is over here. Just paste that value. This. All right, this is what steady state error is. So the time and response expression given by the above value of Ct indicates that for values zeta less than 1, the response presents exponentially decaying oscillations having a frequency omega n under root of 1 minus zeta square. Okay, and the time constants of exponential decay is 1 upon zeta omega n. All right, so this what we are going to get. So here the term, simply write down the terminology over here. So here the term omega n is simply what? Omega n is simply the called as a natural frequency of oscillation, as I have already told this, natural frequency of oscillations. Okay, natural frequency of oscillation. Term omega d, which is omega n under root of 1 minus zeta square we have taken. This is what? Damped frequency of oscillation. Damped frequency of oscillations. All right, the term zeta simply affects the damping, and called damping ratio. This is called damping ratio. This affects the damping. It is affecting damping na? So it is called as a damping ratio. Okay, and the term zeta, omega, and the multiplication of both of these terms is simply called as damping factor. Damping factor, or simply called as the damping coefficient. So the main thing we are going to look into this is simply that the time response of the second order control system, which is given by Ct in the above expression, is influenced by its damping ratio zeta. Is influenced by its damping ratio zeta. So we are getting the different cases. So the cases for the values of damping ratio, that is zeta. So that there are, what are the different cases? Simply the first case is when zeta should be less than 1. Second case we are going to study over there, here should be zeta when it will be equal to 0. Third case when zeta will be equals to 1. And the fourth case we are going to study over here when zeta is greater than 1. So these are the 4 cases which we are going to study, and we are going to have the different responses when after having the different value of the zeta. Okay, so one by one we are going to take it, and let us see what are the responses for the different value of zeta. Okay, first of all, let's take a when the time response, when the value of zeta is less than 1. Okay, so the time response and the error, okay, the time response and the error in the above expressions are plotted. All right, so for zeta less than 1, you can see the time response and the error of a second order control system. Okay, so this is the underdamped case. So you are watching this, so the output is coming, there are the oscillations, it is moving like this. Okay, so these are the oscillation along the line, the output response line, and after a few oscillations at this point, you can see at this point we are getting 0.02%, means the 2%, 98% of oscillations are damped out. We are just having the 2% of oscillations over here. So you can see that the response settles within 2% of the desired value after damping out the oscillations in a time 4t. Okay, we have studied about the t and the 4t, what are all these things. Okay, so the response before this point, before the 98% of the achievement, is called the transient response up to here, and after this is called simply as the steady state response. Okay, so this, in this condition we are getting for zeta less than 1, the time response present damped oscillations. Okay, these are the damped oscillations, and such a response is called underdamped response. This response is called underdamped response. Okay, so for zeta less than 1, we are having the underdamped response. So the second condition we are going to have is simply your zeta is equals to 1. So the value of zeta is equals to 1 we are going to put in the equation number 6.23, which is the equation of Ct. So okay, so Ct, if we are going to put the value of zeta is equals to 1, we will get 1 minus e to the power minus, it was zeta omega nt, so 0 into omega nt divided by under root of 1 minus zeta square, so 0 square, sine, okay, omega n under root of 1 minus zeta square, 0 square instead of zeta, into t, plus tan inverse of under root of 1 minus zeta square, which is 0 square, divided by zeta. Okay, so this we are going to have, this value we are going to have. So simply 1 minus sine omega nt plus tan inverse of infinity. All right, here. So what is this? We will get Ct is equals to 1 minus sine omega nt plus pi by 2. So the value of tan inverse infinity should be equals to pi by 2. Tan theta is equals to infinity at the value of 90 degree. So this is what we will have. So sine omega sine omega nt plus 90 degree, mean sine 90 plus theta is equals to cos theta. So 1 minus cos omega n t. Okay, so CT is this. So what should be the response? The response of CT will be like this. This is the output CT with the time variations t. Okay, so this is 1 unit. This is 1 unit. So response will be what? Response will be like this. Response will be like this. All right. These are simply called as what? Undamped oscillations. What? Undamped oscillations. So we are getting undamped oscillations when zeta is equals to 0. Okay, so this is the second condition. Now we are going to have the third condition, and we have to do detailed, you can see that simplification. So the third condition is C, which is zeta is equals to 1. Okay, so what we will get? We are just going to put that zeta is equals to 1 in equations of CT, the output equation. So CT is equals to, just after putting the value of zeta is equals to 1, and after the simplification we will get the last equation. You can do the simplification, but we didn't need that over here. So just after simplification we will get the value of 1 minus e to the power minus omega n t in bracket 1 plus omega n t. Okay, so this will be the output response when taking zeta equals to 1. So this time response, when we are going to plot this is the line, that is CT over here, T over here. This is the unity input. This is 1 unit. Okay, so we will get like this. Okay, this is 0.02 unit. Okay, so this is the time response of a second order control system when zeta is equals to 1. This is simply a critically damped case. Critically damped condition. Okay, we are getting over here critically damped condition over here. And the fourth condition, the last condition, is what? D, when we are going to have zeta greater than 1. Okay, in this condition also, when we are going to put the value of a zeta greater than 1, so output response should come out to be, so after putting the value of zeta greater than 1 in the equation 6.23, okay, so and making up some difference partial derivative of that, so we will get the final expression as CT is equals to 1 minus e to the power minus zeta minus under root of zeta square minus 1 omega n t, okay, divided by 2 under root of zeta square minus 1 in bracket zeta minus zeta square minus 1, this. Okay, so this is the value of CT. We are going to get this after solving the equation. Okay, so finally what will be the response? This should be the response. This should be the response in this case when the zeta is greater than 1, and this is 0.02 unit, that is 40. Okay, so this response, the time response second order control system when zeta is greater than 1, is simply over damped case. Over damped case. Okay, so we are going to draw all the responses in one graph. So the unit step response, we can write it like this. Okay, so when zeta is less than 1, okay, under damped case we have taken first case we had taken as zeta less than 1, so the oscillations are come out to be like this. Sorry, this must be there. Okay, we are going to have 2%. Okay, after the oscillations we are going to have 0.02 unit. This becomes a steady state condition over here. Okay, so at x zeta is equals to 1, we have critically damped condition, so it gets like this. Okay, and the last condition, when zeta is simply, or you can say that it is greater than 1, so it is simply called as the overdamped condition. We have got the response like this, okay. So what we have simply zeta is equals to 0.5, it is also less than 1. Okay, one more condition we have seen over here like this. This you can see that zeta is equals to 0.8, it is also less than 1. Here what we have, zeta is equals to 1. Okay, and here we have zeta is equals to 2, you can say that, and greater than 1 simply. This is the overdamped condition. So these are the responses we are getting with the different value of zeta with the unit step response, unit step input when we are giving in the control system. All right, so let's see one more thing, which is the transient response specification. Transient response specification. Okay, so in the transient response specification of the second order control system, we are just going to see the time response of an underdamped control system which exhibits damped oscillations. We are having a damped oscillation in this condition, okay, before reaching the steady state condition. So the specifications pertaining to time response during transient part are shown, we are going to see. So what are those things? First of all, we have the rise time. Okay, the rise time. What is a rise time? Rise time is simply denoted by TR, and this rise time is simply the time is simply called as the rise time is from 0 to 100% for underdamped condition. Here you can see that this is the rise time. We can write is like TR. Okay, the rise time is, when we are going to read, the rise time is the time needed for the response to reach from we can also say that 10 to 90% or 0 to 100% of the desired value of the output. So the desired value of the output is this much. So the time taken from 0 to 100%, okay, in the first step, in the underdamped condition. So okay, before the oscillations are taking place, यहाँ ऑसिलेशन हो रहे हैं, तो ऑसिलेशन होने से पहले, सबसे पहले जब ये 0 से 100% पे रीच करा है, दिस टाइम रिस्पॉन्स सिंपली कॉल्ड एज योर राइज टाइम. Second term is simply your peak time, which is denoted by TP. What is this peak time? An underdamped system, simply the underdamped system as shown over here, this system, let me take a different color. So that this system as shown over here, the oscillations are taking place. So in the underdamped system, this presents the oscillations, okay, during transient part. The transient part आपका कहाँ तक होता है? 98% achievement तक. So before in the transient part, okay, so simply the underdamped system presents oscillations during transient part of its response. So at some instant of the time, किसी instant of time पर output आपका exceed कर जाता है जो desired value. Desired value तो आपकी ये है, ये लाइन आपकी बना रखी है जो आउटपुट की डिजायर्ड वैल्यू है, तो वो उससे भी एक्सीड कर जाती है, ठीक है, डिजायर्ड वैल्यू. वाइल एट सम अदर इंस्टेंस द आउटपुट इज लोअर देन इट्स डिजायर्ड वैल्यू. कहीं कहीं उससे कम भी होता है, कहीं कहीं उससे ज़्यादा भी होता है. ओके, सो द मैक्सिमम पॉजिटिव डेविएशन ऑफ द आउटपुट विद रिस्पेक्ट टू डिजायर्ड वैल्यू इज नोन एज मैक्सिमम ओवरशूट एंड इज डिनोटेड बाय सिंपली MP. ओके, MP. सो द टाइम नीडेड, MP सिंपली मैक्सिमम पीक कह सकते हैं आप इसको, ये आपका MP है जो आपका मैक्सिमम पीक है, ठीक है, जो मैक्सिमम ओवरशूट है. तो द टाइम नीडेड टू रीच द मैक्सिमम ओवरशूट, इस मैक्सिमम ओवरशूट पर पहुंचने के लिए जो टाइम आपका लग रहा है, दैट टाइम इज सिंपली कॉल्ड एज द पीक टाइम एंड इज सिंपली डिनोटेड बाय TP ओवर हियर. ऑलराइट, सो दिस इज सिंपली योर पीक टाइम. एंड द थर्ड टर्म इज सिंपली what? Settling time. Settling We have already told you earlier what is the settling time. Settling time is simply the time needed to settle down. You can see that you can say the settling time is simply TS. इट्स सिंपली द टाइम. ये एक दो रिस्पॉन्सेज आपके अभी बताए थे. दो रिस्पॉन्सेज, एक तो आपका ट्रांजिएंट रिस्पॉन्स होता है, उसके बाद में आपका स्टेडी स्टेट रिस्पॉन्स होता है. तो स्टेडी स्टेट रिस्पॉन्स तक पहुंचने के लिए जो टाइम हमें लग रहा है, दैट टाइम इज सिंपली कॉल्ड एज द सेटलिंग टाइम. ओके. फॉर एन अंडर डैम्प सिस्टम द मैग्नीट्यूड ऑफ द ऑसिलेशंस प्रेजेंट इन द आउटपुट रिस्पॉन्स डिके. ये मैग्नीट्यूड इसका जो है आपका डिके कर रहा है. ये यहाँ से ये डिके कर रहा है इसका ऑसिलेशंस का. ओके. इसका मैग्नीट्यूड डिके कर रहा है एक्सपोनेंशियली. तो द टाइम नीडेड टू सेटल डाउन अफोरसेड ऑसिलेशंस विद इन 2%. तो इन ऑसिलेशंस को 2% तक पहुंचने में जो टाइम लग रहा है आपको, दैट टाइम इज सिंपली कॉल्ड एज सेटलिंग टाइम, विच इज रूल्ड बाय TS. So these are the different time responses which we need to specify for a second order control system. Okay, thank you.